Hello, Matthews Gatos here. In this video, I'm going to cover AP Bonus Part 1, which is the linear algebra part. So in 10C, we already did solving systems of linear equations. And there were three different types of systems based on the point that a solution to a system is a point of intersection. So really key that it is a point, meaning it's an x and a y that they have in common. So the first type of a system we could have is an inconsistent solution. This is a set of parallel lines because they are never going to intersect. In fact, parallel lines have so much in common, it's a shame they'll never meet. The second system is a dependent system, and this is infinite solutions because it's one line drawn on top of another line. So they are always intersecting because they're the same line, so there are infinite solutions. So no solution, infinite solutions, or in this last one, independent, I can have one single solution, which is the point of intersection. So now we're going to solve a system of equation with three equations, three unknowns. Adding on that third equation changes it from a two-dimensional system to a three-dimensional system. So we're not talking about lines of intersection, lines intersecting, we're talking about planes intersecting. So this would be the XYZ plane, and the best way for me to illustrate this to you is by using a rectangular prism. So it's kind of like I want you to imagine a room in your house or your bedroom, and you have two walls. So you have a wall here, and you have a wall here, and then you have a floor. So where these two walls and the floor all meet would be the solution. So the solution would actually be that point there, X, Y, and Z. So it's still a point of intersection, but it's a point that's common to all three planes. So similar to linear equations, there are three types of systems. The first system is consistent and independent. There is a single solution. It's that point of intersection right there, and it has coordinates of X, Y, Z. We need to state it as a coordinate. The second type of system is a consistent but dependent solution. The reason it's dependent is because it's a line of intersection. So you can see that all these planes intersect in a line. So it's infinite number of systems or solutions because you have X and Y, which is a line, and lines have infinite points on them. So this solution has infinite solutions. It's dependent because it depends on the values of X and Y. And the third type of system that you can have is called an inconsistent system, which is no solution, meaning that all three planes don't intersect. So you can see in this example here, we have two of the planes intersecting and two of the planes, but we don't have all three. This one here, we just have two of the planes, the orange with the green, the orange with the blue. And in this last example, none of the planes intersect. So those are the three different types of systems that we'll be looking at. So how do you solve a system of equations with three unknowns? Well, the process is very similar to two. It's just one extra step. When we had a system with two equations, two unknowns, we used elimination to get it down to one equation, one unknown, and then we took that unknown and went backwards up the chain to figure out the other solutions. We're going to do the same thing. So we're going to start with three unknowns, and through elimination, we are going to get it down to a system of two unknowns. And then we're going to go down to one unknown and then fill it back upwards. So we're going to back substitute upwards. Again, the most important part of solving any of these questions is the check. So please don't forget to do your check. Let's look at this first example here. So I want to solve this system. Now, I want to go from three equations to two equations to one equations, but I just wanted to start small. And you can see that I have already the solution to one of my variables, which is Z. So I'm going to use that and I'm going to back substitute here to figure out what y is. So I have y minus a half of z, which I now know is -1, equals to 4. So y plus a half equals 4, and then subtract a half from both sides, and we get 4 take away a half is 3.5, or as a fraction, 7 halves. I would probably list it as a fraction because my question started with fractions. And then I'm going to take x and y together and back substitute here to figure out what x is. So I have x minus 1/3 of y plus 1/2 of z equals 1. So x minus 7/6 minus 1/2 equals 1. So we're going to go ahead and solve this. So x minus, well, 7/6 take away 3/6 using a common denominator is really 10/6 equals 1. So then I'm just going to simplify this as 5/3 equals 1 and add 5/3 to the other side. So 3 over 3 plus 5 over 3, x will equal to 8 over 3. So now I've got my x, y, and z. Now I need to state my solution. Really important. Don't forget to state it. That is not a stated solution. So the solution is a point of intersection in alphabetical order. It is x and y and z. So this is my solution. So as with this and every equation that I do with you guys, I always really recommend that you go and check. So over here, you can see here's my check. And I substitute it into the first equation. I get the correct answer I'm supposed to get. And I substitute my values into the second equation. And I also get the value I was supposed to get. So I know I'm correct. Okay, let's up the difficulty just a little bit more. This time we're going to do a system of equations with 3 unknowns, but then you can see I have 2 systems that have 2 unknowns. So I'm going to start with those first and eliminate one of the variables. Now it doesn't really matter which variable you eliminate, so choose whichever one that you think is the easiest. So for me right now, the y's are opposite values, so I'm going to choose to eliminate by adding these 2 equations here. So just for simplicity's sake, let's label this equation A, this equation B, and this equation C, just so that I can communicate effectively what I'm doing. So what I'm really doing is I'm taking equation B and I'm adding it to equation C. And this kind of labeling gets us set up for doing it with matrices, just so that anyone who looks at your solution knows what you're doing. Okay, so I've chosen to add B and C together because that will eliminate my variable y, because negative 2y plus 2y is 0. So z plus negative 2z is negative z, and then 6 plus negative 12 is negative 6. Divide both sides by negative 1, and you get your first value, which is z is equal to 6. So now I know that z is 6. I'm going to back substitute into my other equation to figure out what y is. So I'll go into equation B, and in equation B, I will do negative 2y plus z, which is 6, equals 6. So negative 2y plus, subtract 6 from both sides. So subtract 6 from both sides, and this equals 0. Divide both sides by negative 2, and this equals 0. So we've got z, and we've got y. And now I'm going to back substitute into equation 1. So x minus y plus z equals 5. So x plus 6 equals 5. Subtract 6 from both sides, and you get x is equal to negative 1. So again, that is not the solution. The solution is a point of intersection, so you always need to state your solution as a point in alphabetical order. So my solution is negative 1, 0, and 6. So let's look at that on the next page where I've done my check and just see if we are correct. So this is what we thought the solution was. You can see I substituted the values into the first equation. It worked. I substituted the values of y and z into this equation, and y and z into this equation, so I know I've done it correctly. It has to work for all 3 equations, not just one. Okay, so now let's try one where there's legitimately 3 equations, 3 unknowns. So again, for simplicity, I will label those as A, B, and C. So I would use equation A because the coefficients of every variable are 1, and I would use it in conjunction with the equations B and C. So, and again, there are several ways of solving this, so don't think that my way is the only way, because it most certainly is not. This is just kind of the way I see it, but you guys might see it differently, but we'll end up with the same answer if we've done it correctly. So I'm going to do 6 times equation A, which is 6x plus 6y plus 6z equals 12. Don't forget to multiply the constant. And then I'll combine that with equation B. Okay, so in doing that, you can see I can combine those equations to actually get rid of x. And that's exactly what I'm going to do. So subtract them all term by term. So I'm going to do 6x take away 6x is 0. 6y take away a negative 4y is 10y. 6z take away 5z is z. And 12 take away 31 is negative 19. Okay, so I've got one equation with 2 variables. I need another one to go with it. So let's repeat this process again. So this time I'm going to do 5 times equation A and add it on to, or sorry, subtract from that equation C. Okay, so over here, 5 times equation A, so that will be 5x plus 5y plus 5z equals 10. And then right underneath it, I'll write my equation C because I have chosen to eliminate x from both of these. And now I just subtract these term by term. So 5x take away 5x is 0. 5y take away 2y is 3y. 5z take away 2z is 3z. Equals 10 take away 13 is negative 3. Okay, so looking at that equation, I can leave it like that, or it would make my life a lot easier if I just divided everything by 3. So if I divide everything by 3 in this equation, and I mean everything including the constant, I end up with y plus c equals negative 1. Now, the reason I did that is because now I have a coefficient of 1 for each of my variables. So I'm going to call this equation D and this equation E. So I want to go from, I've gone from 3 down to 2. I now need to go down to 1 equation. So looking at those 2 equations, let's write out one on top of the other. So equation D and E, doesn't matter which one you put first or second. Negative 19 and y plus c equals negative 1. I can see I can eliminate my z variable by subtracting. So 10y take away y is 9y. Z take away z is gone. Negative 19 take away negative 1 is negative 18. And then I just have to divide y by 9 on both sides, and I get y is negative 2. Okay, so now that I have y is equal to negative 2, I just have to back substitute into all my other equations to figure out the other values. So let's go to equation E, and y is negative 2 plus z equals negative 1. So add 2 to both sides, and z is equal to 1. So now I've got y and I've got z, so I'm going to go back into equation A. So back into equation A, and I'm going to figure out what x is. So I have x plus y plus z equals 2. So this is really x plus negative 1 equals 2. So what I would do here is I would add 1 to both sides and get that x is equal to 3. So again, this is not my solution. My solution is a point of intersection in alphabetical order, x, y, and then z. So let's copy this equation over, and I'm going to show you my check just to see if I did that correctly. So I'm going to take this point and I'm going to put it into my original equations. So you can see when I have x plus y plus z equals, and it's supposed to equal 2, that's good. And then my second equation plugging in 3, negative 2, and 1 also is good. And then my last equation has to work for all of them. So definitely check all of them and show a check for all of them. Okay, let's try something a little bit different in this one. So we've seen where we have 1 equation, we've seen where we have 2 equations, 2 unknowns. The last one was all 3 equations, 3 unknowns with a unique solution. Let's look at this one and see what happens here. So looking at this again, I'm going to label them as A, B, C. And I am going to use my equation C, where there is coefficients of 1 for all of them, to eliminate the other ones. So I will do 2 times equation C, and I'm going to subtract from that equation A. So 2 times equation C is 2x minus 2y plus 2z equals 0 times 2, also 0. And then directly under that, I'll write equation A. And then I'll subtract. So 2x take away 2x, gone. Negative 2y take away y, negative 3y. 2z take away a negative 3z is a positive 5z. And 0 take away 0 is 0. Okay, let's do this again. So I'm going to do this time 4 times equation C, and I'm going to subtract from that equation B. So 4 times equation C, 4x minus 4y plus 4z equals 4 times 0 is still 0. And directly under that, I'll write my equation for B. 4x take away 4x, 0, gone. Negative 4y take away 2y is negative 6y. 4z take away a negative 6z is a positive 10z. And 0 take away 0 equals 0. Okay, so at this point here, I'm going to label this one equation D and this one equation E. And what I notice in equation E, to make it a little bit easier, is 2 is a common factor of everything. So I'll divide everything by 2. So my equation E becomes negative 3y plus 5z equals 0. So I'm going to put equation D and E together. So equation D and equation E. And hopefully you can notice those are the exact same equations. So if I subtract them term by term, no, yeah, I will subtract them because they're the same here. So negative 3y take away negative 3y is 0, plus 5z take away 5z is 0, equals 0 take away 0 is 0. So all my variables go away, which definitely tells me I have not one solution. So because 0 equals 0, now it doesn't always have to be 0 equals 0. You could end up with like 2 equals 2 or 4 equals 4. You end up with a true statement. And this true statement is always true. So this is always true, which means that there are infinite number of solutions. So if you reach a statement like this where you have a true statement, that means that there are infinite solutions. Kind of like parallel solutions in chapter or in 10C when we did the systems of equations. Let me just take you back to the systems that I was explaining and show you why it would be infinite solutions. So really what we have here when we end up with a true statement is this one right here. Okay, so it's consistent and it's dependent. So really what that would tell you is it would be a line of intersection. So an intersection point that is a line, which means that there are an infinite number of solutions, all dependent on the values of x and x. So a consistent dependent solution happens when all my variables are canceled out and I end up with a true statement. So when I end up with a true statement with no variables. Okay, that will be what a consistent dependent system looks like. Okay, so let's look at our last example together. This one here. So again, I am going to use the labeling system, ABC. I find that's really useful. And I see right away I can do equation A plus equation B to eliminate x because they're the same but opposite. So that's what I'll start with. And because they're opposite values, I'm going to add. So x plus negative x is 0. Negative 3y plus 2y is negative y. Z plus negative 5z is negative 4z. And 4 plus 3 is 7. Okay, so I'm going to look at, let's look at equation A. I'm going to multiply that by 5. 5 times equation A. And I'm going to add that to equation B. No, I'm going to add that to equation C. My mistake. C. Okay, so 5 times equation A. 5x minus 15y plus 5z equals 20. And then equation C, I'll write that underneath. Oh, and I'm not going to add. I can see that right now. I'm going to subtract. Okay. Work with me, pen. Oops, a daisy. Let's try that again. There we go. Okay, so 5x take away 5x, gone. Then I have negative 15y take away negative 13y is negative 2y. 5z take away 13z, that's negative 8. And 20 take away 8 is 12. So I notice that everything here is divisible by 2. So just to make my life a little simpler, I'm going to divide each of my terms by 2. So I end up with negative y plus 4z equals 6. So I'll call this equation D and this one equation E. And I see they have the same y value, so I can probably eliminate that by subtraction. And we'll do exactly that. So negative 4 minus 4z equals 7. And then negative 4 minus 4z equals 6. Ah, this looks very similar to the last question. Let's look at the last question again. See how I had same, 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 always true. Over here, we have same, 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 not the same. So let's see what's going to happen here. So I'm going to subtract these. So negative y, take away negative y is 0, it's gone. Negative 4z, take away negative 4z, 0, it's also gone. 7, take away 6 is 1. So I end up with a statement, no variables, 0 equals 1. Well, is that true? Does 0 equal 1? Hopefully you're saying no. Okay, so I end up with a statement that is always false. So I am ending up with a false statement. So if I end up with a false statement, that tells me I have no solution. So 2 of the planes might intersect, but all 3 for sure don't intersect. So let's go back to our systems again just to look at this one. So this is an example of this system here, no solution. Okay, so we don't have a point for all 3. So in this case here, you're going to end up with a false statement, again with no variables. So that illustrates all 3 types of systems that you can have: consistent, consistent dependent, and inconsistent. So I hope you guys really enjoyed linear algebra as much as I did. I absolutely love it. And to be honest with you, if I had $1 for every time algebra has helped me, well, I would have myself X dollars. Okay, so what you guys can do now is work on your assignment. I have 4 questions for you to do. Make sure you show all your work, clearly state your answer as a point, and show your check. I hope this video helped you, and I look forward to seeing you for the next one.